What if everything we think we know about the history of technology is incomplete? Picture this: long before Newton described gravity, before Faraday unlocked the secrets of electromagnetism, and long before the very foundations of modern science were even dreamed of, ancient innovators were building machines that shouldn't have been possible. They crafted devices of breathtaking complexity, objects that harnessed natural forces in ways that still leave researchers scratching their heads today. These weren't just simple tools or lucky accidents. They were precise, sophisticated, and in some cases, so advanced that we've only just begun to reverse engineer their secrets centuries or even millennia later. From the depths of the Mediterranean Sea to the deserts of the Middle East, from the highlands of Peru to the palaces of Byzantium, these forgotten marvels whisper a story of human ingenuity that defies conventional timelines. Think of the Antikythera mechanism, an intricate bronze computer with gears that tracked the stars, or the Baghdad battery, a humble clay jar that might have generated electricity 2,000 years before the first modern battery was invented. These artifacts aren't just curiosities, they're windows into a lost world of knowledge, a world where observation, intuition, and relentless experimentation led to breakthroughs that seemed to bend the rules of physics itself. In this video, we're going to explore 28 of these extraordinary inventions, devices that worked even before we understood why they worked. We'll journey across civilizations and centuries, meeting the minds and hands that built the seemingly impossible. This isn't just a tour of ancient tech, it's an investigation into the very nature of discovery. How did they do it? What did they know that we've since forgotten? And what does their genius reveal about our own relationship with innovation and mystery? By the end, your view of history and humanity's place in it may never be the same. So settle in, open your mind, and let's travel back through time to uncover technologies so advanced they feel almost like magic. Long before Newton formulated his laws of motion or Faraday discovered electromagnetic induction, ancient civilizations were quietly conducting experiments that would one day be considered revolutionary. These were not laboratories in the modern sense, but workshops, temples, and royal courts where innovation was driven by immediate need and profound curiosity. The ancient Egyptians developed precise water clocks to track the hours of the night for religious ceremonies, while the Maya crafted intricate astronomical instruments to predict celestial events essential to their cosmology. These cultures weren't working from a textbook of physics, they were learning directly from the world around them, through meticulous observation and relentless trial and error. This hands-on approach to discovery meant that progress was often incremental, built upon generations of accumulated craft knowledge rather than sudden theoretical breakthroughs. A Mesopotamian potter might have noticed a certain glaze conducted heat differently, or a Roman engineer might have stumbled upon a concrete formula that set underwater by experimenting with different volcanic ashes. Their goal wasn't to uncover the fundamental laws of nature, but to solve a specific problem: how to build a more durable aqueduct, how to create a weapon that could burn on water, or how to tell time after sunset. The value was placed overwhelmingly on practical application. If something worked, it was adopted and refined, even if no one could fully explain why it worked. This very practicality, however, made these advancements incredibly vulnerable. Technological knowledge was often held by a small group of master artisans or kept as a state secret, protected for its strategic advantage. When war, famine, or political collapse disrupted these societies, that specialized knowledge could vanish almost overnight. The recipe for Greek fire died with the fall of Constantinople. The precise metallurgical techniques for Damascus steel were lost as the trade routes that supplied the unique Wootz iron from India were disrupted. In other cases, an invention was simply so far ahead of its time that it wasn't fully understood or replicated. The Antikythera mechanism, as we'll see, was a marvel of engineering that had no contemporary equal and wouldn't be matched for over 1,000 years. It wasn't that the device was forgotten, it was that the world around it wasn't yet ready to build upon its genius. Understanding this historical context is crucial. It allows us to see these devices not as inexplicable anomalies or proof of alien intervention, but as brilliant products of their environment. They emerged from cultures that possessed deep patience, sharp observational skills, and a willingness to experiment relentlessly. They represent the pinnacle of what can be achieved when human ingenuity is focused on a problem, even without a formal scientific framework to explain the results. This foundation of practical mastery sets the stage for us to truly appreciate the individual marvels. We're about to explore artifacts that didn't just work despite a lack of modern theory, but operated on principles that wouldn't be formally understood for centuries to come. Now, let's turn our attention to one of the most spectacular and humbling discoveries ever made. A device so advanced it single-handedly rewrote our understanding of ancient technological capability. In 1901, sponge divers exploring a Roman-era shipwreck near the Greek island of Antikythera stumbled upon a corroded lump of bronze and wood that seemed utterly unremarkable at first glance. It was only years later, as museum conservators began to carefully clean the object, that its true nature began to emerge. This was no simple statue or ornament. It was an intricate mechanical marvel, a complex clockwork of interlocking gears housed in a wooden frame, now known as the Antikythera mechanism. Dating back to approximately 100 BC, this device is now recognized as the world's earliest known analog computer. Its purpose was breathtakingly sophisticated, to model the cosmos itself. By turning a hand crank on the side, an operator could advance the mechanism through time, and a series of dials and pointers on the front and back would display the predicted positions of the sun, the moon, and known planets against the backdrop of the zodiac. It could forecast solar and lunar eclipses with remarkable accuracy, and one of its dials even tracked the 4-year cycle of the ancient Olympic Games. This wasn't just a calendar, it was a portable, mechanical representation of the heavens, a simulation of time and celestial motion. What truly separates the Antikythera mechanism from any other known artifact of its era is its breathtaking mechanical complexity. Modern imaging techniques like X-ray tomography have revealed a labyrinth of at least 37 precise bronze gears working in concert. The most astonishing of these is a differential gear, a sophisticated assembly that calculates the difference between two rotational inputs to produce a third output. This technology was thought to have been invented in the 16th century for use in automobile transmissions, yet here it was, sitting at the bottom of the sea for 2,000 years, used by the Greeks to accurately model the moon's irregular orbit. The mechanism accounted for the fact that the moon travels at different speeds at different points in its ellipse around Earth, a subtlety known as orbital eccentricity. This understanding of lunar motion wouldn't be formally described with mathematical laws until the work of astronomers like Johannes Kepler in the 17th century. The existence of this device forces us to completely reconsider the technological landscape of the ancient world. This level of precision engineering and profound astronomical insight didn't appear in a vacuum. It suggests a previously unknown tradition of high craftsmanship and scientific instrument making in ancient Greece. The mechanism's design implies it was not the first of its kind, but rather a refined version built upon generations of prior experimentation and knowledge. The genius of its creators lay in their ability to translate centuries of meticulous astronomical observation, a purely intellectual pursuit, into a tangible mechanical reality. They may not have had Newton's laws of gravitation or a complete theory of orbital mechanics, but through patient observation, they discerned the patterns of the cosmos and found a way to replicate them in bronze and gear teeth. The Antikythera mechanism stands as a powerful testament to the fact that you don't need to fully understand the underlying physics of the universe to harness its patterns and build something truly extraordinary. While the Antikythera mechanism reveals a sophisticated understanding of mechanics and astronomy, another discovery from the ancient world hints at a completely different type of knowledge: the mastery of electrical energy. In 1936, during excavations near Baghdad, workers uncovered a seemingly mundane set of objects that would later become one of archaeology's most enduring puzzles. The find consisted of a small terracotta pot, roughly 13 centimeters high, housing a rolled copper sheet that formed a cylinder. Sealed at the top with asphalt or bitumen, this plug held an iron rod suspended perfectly down the center of the copper tube. To the untrained eye, it looked like a sealed storage jar, perhaps for scrolls or spices. But to Wilhelm Koenig, the German archaeologist who first studied it, the arrangement looked strangely deliberate, almost like a primitive chemical cell. Dating these artifacts is tricky, but most experts place their creation somewhere between 250 years before the Common Era and 250 years after, during the Parthian or Sassanid periods. The real mystery begins when you imagine filling that clay jar with a common acidic liquid of the time, perhaps vinegar, grape juice, or even wine. The iron rod and copper cylinder, separated by the electrolyte, create a classic galvanic cell. The iron willingly gives up electrons, oxidizing as it dissolves slightly into the acidic solution. These electrons then travel through the electrolyte to the copper, creating a measurable electrical potential difference between the two metals. In simple terms, it becomes a battery capable of producing a modest but consistent voltage of around 1 volt. Connect several of these jars together in a series, and you could theoretically generate enough power for a noticeable effect. This is where the fascinating debate among historians and archaeologists ignites. If it was indeed a battery, what on earth was it used for? One compelling theory suggests electroplating, the process of using electricity to bond a thin layer of a precious metal, like gold, onto the surface of a less valuable object, like silver or copper. Artisans could have used the battery's gentle current to gild small jewelry or religious artifacts, a practice that would explain the presence of finely gold-plated objects from the region that lack any signs of traditional mercury-based fire gilding. Another, more speculative idea proposes a medical application. Ancient texts describe using electric fish to numb pain or treat ailments. Perhaps these cells provided a more controllable source for similar electrotherapy. A third, and perhaps most intriguing possibility, is that they were used for religious or mystical ceremonies. Imagine a statue in a dim temple, with wires connected to hidden batteries causing a faint tingling sensation or a mysterious glow when touched by a devoted initiate. It would have been a powerful tool for priests to demonstrate divine presence. Skeptics, of course, offer alternative explanations. They argue the device could have been a simple storage jar for sacred scrolls, with the iron rod merely acting as a rust-resistant roller for the parchment, and the asphalt seal protecting the contents from moisture. The problem with this theory is that the asphalt seal completely encases the top, making the contents inside utterly inaccessible without breaking the jar open. Why go to such trouble to hermetically seal something you intended to use regularly? The very design suggests the jar was meant to be filled and refilled with a liquid. The most profound aspect of the Baghdad battery isn't necessarily proving its definitive use, but rather acknowledging its mere possibility. It represents a tantalizing what-if. It shows that the fundamental components for understanding electricity, different metals, electrolytes, and the concept of a circuit were all present and being manipulated. Even if its creators didn't have a theory of electrons or electromotive force, they could have been experimenting with the practical effects of this mysterious invisible energy. It stands as a powerful symbol of empirical discovery, a testament to the idea that you can harness a phenomenon long before you can write the textbook that explains it. Now, let's shift our focus from the subtle currents of electricity to the terrifying spectacle of uncontrolled fire, specifically, a weapon so formidable that it literally shaped the fate of an empire. As the Byzantine Empire found itself under constant assault in the 7th century, particularly from the rapidly expanding Arab fleets, its survival hinged on a technological marvel that must have seemed like a gift from the gods themselves. This was Greek fire, a legendary incendiary substance that became the Byzantines' most closely guarded secret and their ultimate naval advantage. Imagine the sheer terror of facing this weapon in battle, a liquid flame that roared from the prows of Byzantine ships, not just burning but clinging to everything it touched. Most horrifying of all, it could blaze across the surface of the water itself, turning the sea into a sheet of fire that would engulf enemy vessels. Attempts to douse it with water were not just futile, they often made the inferno spread even more violently. For centuries, this terrifying technology allowed the outnumbered Byzantine navy to defend its capital, Constantinople, against overwhelming odds, creating an aura of invincibility that was as much psychological as it was tactical. The exact formula for Greek fire, known to the Byzantines as sea fire or liquid fire, was such a closely held state secret that its precise composition was lost to history and remains one of archaeology's greatest unsolved mysteries. What we understand comes from historical accounts and modern chemical detective work. The primary ingredient was almost certainly crude petroleum, likely sourced from natural oil seeps around the Black Sea region. But raw oil alone doesn't explain the weapon's most fearsome properties. Historians and chemists now believe the mixture was a complex brew that probably included other potent additives. Quicklime, for instance, heats up spontaneously when it comes into contact with water, which could have helped ignite the mixture upon impact. Sulfur would have lowered its ignition temperature and produced thick, choking fumes. Perhaps resin or pitch was added to make the sticky, adhesive quality that made it so difficult to remove from ships' armor and skin. Some theories even suggest the addition of saltpeter, a key component of gunpowder, though this remains debated. The mixture was then pressurized in heated bronze tanks on Byzantine ships and projected through a tube called a siphon, where it was likely ignited by a permanent flame at the nozzle, creating a primitive but devastating flamethrower. What makes Greek fire truly remarkable from a scientific perspective is that its creators were manipulating chemical properties that wouldn't be formally understood for over 1,000 years. The Byzantines had no periodic table, no theory of oxidation, and no concept of the chemical reaction chains they were initiating. Yet they empirically discovered how to create a substance with pyrophoric qualities, meaning it could ignite spontaneously upon contact with air or water. They also understood hydrophobic principles. The fact that the fire burned on water suggests they somehow devised a way for the petroleum mixture to vaporize and ignite on the water's surface rather than being smothered by it. This practical mastery of combustion chemistry, born out of desperate military necessity, allowed them to create a weapon that effectively bypassed the contemporary understanding of how fire behaved. They weren't applying scientific theory, they were relentless experimenters, probably testing countless combinations of flammable materials until they found one that produced these nightmarish, almost supernatural effects. The secret was so valuable that, according to legend, the recipe was handed down from emperor to emperor, and its creators were sworn to absolute secrecy on pain of death. This intense protection ultimately led to the knowledge being lost, perhaps during the chaos of the Fourth Crusade's sack of Constantinople in 1204. Today, we can only reverse engineer the possibilities, a testament to how practical innovation, driven by immediate need, can leapfrog far ahead of theoretical science, creating technology that seems to defy the very laws of nature as they were understood at the time. Now, let's voyage from the burning seas of Byzantium to the fog-shrouded waters of the North Atlantic, where the Vikings faced a navigational challenge that would have stalled most sailors of their era. How did they manage to cross vast, empty stretches of ocean, like the treacherous journey from Norway to Greenland, without the sun to guide them? The sagas hold a cryptic clue, a magical tool called a solarstein or sunstone. These ancient texts describe legendary figures like Sigurd using this stone to locate the hidden sun through dense cloud cover or even hours after it had set below the horizon, revealing its precise direction. For centuries, historians dismissed these accounts as pure myth, another fantastical element of Viking lore. But modern science has revealed a stunning possibility that the Norse were not just skilled sailors, but masters of an advanced optical technique that wouldn't be formally understood for hundreds of years. The key to unlocking this mystery lies in a common crystal, Iceland spar, a transparent form of calcite found in Scandinavia. This remarkable mineral has a property known as birefringence. It splits a beam of light into two separate rays. When you hold a piece of calcite up to the sky and look through it, you don't see one image but two. Even on a completely overcast day, sunlight becomes partially polarized, meaning its light waves vibrate in a specific direction as they scatter through the atmosphere. The Vikings, through brilliant empirical observation, could have discovered that by rotating a calcite sunstone, they could make these two faint images change in intensity. When the two light beams appeared equally bright, the crystal's alignment would point directly toward the hidden sun's position, effectively giving them a celestial compass regardless of the weather. This practical method of navigation is a perfect example of using a phenomenon long before comprehending its underlying cause. The Vikings didn't need to understand the wave theory of light or the physics of polarization. They simply needed to know that the crystal worked. It was a tool born from relentless experimentation and sharp observation, a functional solution to a life or death problem. It allowed them to venture far from the safety of coastal landmarks, confident they could maintain their course. The genius of this technology is its beautiful simplicity. Unlike the complex gears of the Antikythera mechanism, the sunstone required no manufacturing. It was a natural object whose hidden property was unlocked through applied knowledge. Recent archaeological findings lend weight to this theory. A calcite crystal was discovered aboard a 16th century English shipwreck, suggesting the technique might have persisted long after the Viking Age. Even more compelling, in 2013, a team of researchers proved the method's astounding accuracy, demonstrating that using a sunstone to take bearings on the sun could navigate within a margin of error of just a few degrees, even when the sun was well below the horizon. The Vikings' legendary navigational prowess, once attributed to myth and luck, now appears to be grounded in a sophisticated and repeatable scientific practice, making them the undisputed masters of the medieval seas. While the Vikings mastered navigation using light itself, an inventor in Roman Egypt was exploring a far more tangible force, the power of steam. In the 1st century of the Common Era, in the great city of Alexandria, the brilliant engineer and mathematician Heron created a device that seems to leap centuries ahead of its time. He called it an Aeolipile, named after Aeolus, the Greek god of the winds. At first glance, it appeared to be a simple, hollow bronze sphere, mounted on a pair of tubes that connected it to a heated water reservoir below. But projecting from opposite sides of this sphere were two L-shaped nozzles, bent at precise right angles. Heron would instruct a temple acolyte to light a fire beneath the kettle. As the water reached a rolling boil, steam would forcefully rise through the tubes and fill the sphere, building pressure with nowhere to go except through the two narrow nozzles. And then something magical would happen. Jets of high-pressure steam would scream out of those nozzles, and in doing so, they would push back against the sphere with equal force. This action, paired with an equal and opposite reaction from the escaping steam, would set the entire sphere into a frantic, whirling rotation, faster and faster until it became a blur of spinning bronze and hissing vapor. To any observer, it must have looked like a divine wonder, a captured tempest made to dance for human amusement. Heron himself documented the Aeolipile in his work Pneumatica, but he categorized it among his theatrical automata and temple marvels, devices designed to inspire awe and reinforce religious belief. There's no evidence that he or any of his contemporaries saw it as a source of usable work. It was a fascinating toy, a philosophical demonstration, but not an engine to power industry. And this is perhaps the most poignant aspect of its story. Heron was standing on the very brink of an industrial revolution, holding all the necessary components in his hands: a heat source, water, steam, and a mechanism to convert thermal energy into kinetic, rotational motion. He had, in essence, built the world's first reaction steam turbine, a principle that would not be reinvented until the 17th century and would not begin to power the world until the 18th. The fundamental physics at play were Newton's third law of motion: for every action there is an equal and opposite reaction, and the basic principles of thermodynamics governing the conversion of heat into work. Yet these concepts would not be formally defined and published for another 1700 years. The Aeolipile stands as a profound testament to a different kind of genius. Heron wasn't a theoretical physicist. He was a master engineer and an empiricist. He understood these principles implicitly through observation and experimentation. He didn't need the abstract law to know that if you push a fluid out in one direction, it will push you in the other. He could see it, hear it, and make it happen. His work represents the immense power and the frustrating limitation of purely practical knowledge. The ancient world possessed the mechanical brilliance to conceive of such a device and the metallurgical skill to craft it, but it lacked the socioeconomic conditions, like a need to replace manual labor or a culture of widespread technological adoption, that would have been necessary to see its true potential. The steam engine wasn't born from a single eureka, a moment, but from a slow convergence of theory, necessity, and engineering. Heron had the engineering in spectacular abundance, but the world around him wasn't ready to provide the theory or the necessity. His wondrous spinning sphere remains a breathtaking glimpse of a path not taken, a revolution that could have been, had the pieces fallen into place differently. It is a brilliant, whirring question mark in the history of technology, challenging our assumptions about progress and reminding us that seeing a phenomenon is only the first step. Understanding how to change the world with it is another matter entirely. While Heron in Alexandria was harnessing steam and Viking navigators were reading the hidden sun on the other side of the world, a brilliant Chinese scholar official was turning his attention to a far more destructive and unpredictable force of nature, the earthquake. In the year 132 of the Common Era, during the illustrious Han Dynasty, Zhang Heng presented the court with a device that must have seemed like something from mythology. He called it the Hufeng Didongyi, an instrument for inquiring into the wind and the motion of the earth. To the modern eye, it was a breathtaking work of art and engineering, a large bronze urn nearly 2 meters in diameter, adorned with 8 dragons snaking down its sides, each poised above a corresponding bronze frog with its mouth wide open. Its beauty, however, was secondary to its utterly bewildering function. Zhang Heng claimed this vessel could not only detect an earthquake from hundreds of miles away, but it could also point in the direction of the cataclysm. To a court accustomed to viewing earthquakes as divine omens or punishments, the idea of a machine that could objectively measure such an event was nothing short of revolutionary. The device operated with a beautiful, almost theatrical simplicity. Inside that ornate bronze jar, modern reconstructions suggest, hung a heavy inverted pendulum, a large mass suspended from a central pillar. This pendulum was delicately connected through a series of levers and mechanisms to the heads of the 8 dragons. When the earth remained still, the pendulum hung motionless and the dragons held their bronze balls tightly. But when the first faint tremors from a distant quake rippled through the ground, they would set the heavy pendulum swinging. Its inertia, its tendency to stay at rest while the world moved around it, would cause it to lag slightly behind the motion of the urn itself. This subtle differential movement would be amplified by the internal levers, triggering a release mechanism in one of the dragons. A ball would drop from its jaws, clattering loudly into the mouth of the waiting frog below. The specific dragon that released its ball indicated the compass direction from which the seismic waves originated, providing officials with a crucial first alert. Historical records tell of one occasion where the device triggered a dragon to the west, yet no tremors were felt in the capital. Skeptics dismissed it as a failure, until days later a messenger arrived from a province far to the west, reporting a devastating earthquake. The seismoscope had detected it from a distance of over 400 miles. The sheer brilliance of Zhang Heng's invention lies in the physical principles it unknowingly exploited, concepts that would remain formally undefined for over 1,500 years. The heavy central pendulum was a masterful application of inertia, the property of matter that Isaac Newton would later codify as his first law of motion. The pendulum's mass resisted the sudden movement of the ground, allowing the device to sense the slightest seismic shudders. Furthermore, the entire system was a crude but effective seismometer, responding to the different types of seismic waves that travel through the Earth. The primary waves, or P waves, which are faster but less destructive, would likely have been the first to reach the capital, triggering the initial pendulum motion. The device was essentially listening for these early warnings. Zhang Heng and his contemporaries had no concept of wave propagation, harmonic motion, or structural dynamics as formal sciences. They couldn't mathematically describe why the pendulum swung or how the energy traveled through the ground. Their understanding was purely empirical, born from centuries of observing how the Earth behaved during tremors. They noticed that certain structures swayed, that objects could be shaken from shelves, and they applied these observations to create a functional detection tool. It was a solution engineered from effect rather than from cause. Zhang Heng's seismoscope stands as a monumental achievement in predictive technology, a device that transformed the mysterious and terrifying rumble of the Earth into something that could be measured, recorded, and acted upon. It gave a nervous empire a precious head start, allowing aid and resources to be directed toward disaster zones with a speed that would be impressive even today. It proves that you don't need to fully understand a force's deepest secrets to learn how to listen for its approach. Shifting our focus from the predictive power of Zhang Heng's Seismoscope, we arrive at one of history's most enduring and spectacular tales of ancient ingenuity under siege. The scene is Syracuse, Sicily, in the year 214 before the Common Era. The formidable Roman fleet, under the command of General Marcus Claudius Marcellus, has surrounded the city, its wooden warships filling the harbor in a show of overwhelming force. The city's chief defender is the legendary mathematician and inventor Archimedes. According to accounts written centuries later by authors like Lucian and Anthemius of Tralles, the aging genius did not just rely on conventional weapons. He is said to have deployed a device of breathtaking audacity, a massive array of highly polished bronze shields or mirrors, arranged on the city walls and angled to reflect the intense Mediterranean sun onto the Roman ships. The story goes that these concentrated beams of sunlight converged onto a single point on the hulls and sails, heating the wood until it smoldered and burst into flame, turning the Roman fleet into a terrified inferno and repelling the invasion through the power of the sun itself. For centuries, this account of Archimedes' heat ray has been relegated to the realm of myth and legend, a fantastical story that seemed to defy the practical limitations of ancient technology. The primary skepticism stems from the historical sources themselves, which were written hundreds of years after the event by authors who were not eyewitnesses. Furthermore, the feat requires a level of precision that seems almost superhuman. To successfully set a ship on fire, the mirrors would need to maintain a perfect focus on a small, moving target hundreds of meters away, all while the ships rocked on the waves and the sun moved across the sky. Critics have long argued that the atmospheric conditions, the imperfect reflectivity of bronze, and the sheer organizational chaos of a battle would make such a weapon impractical, if not entirely impossible. They suggest the story is more likely a powerful metaphor for Archimedes' intellectual brilliance, a legend that grew in the telling to emphasize how his mind was a weapon more powerful than any army. Yet the story refuses to die, largely because modern scientific inquiry has repeatedly shown that the fundamental concept is not just possible, but demonstrably effective. The most famous test was conducted by the Greek engineer Ioannis Sakkas in 1973, using 70 polished bronze mirrors, each about 1.5 meters by 1 meter, held by sailors from the Greek Navy. Sakkas was able to focus the sun's rays on a wooden mock-up of a Roman warship anchored 90 meters away. Within seconds, the wood began to smoke, and moments later, flames erupted. The Massachusetts Institute of Technology took up the challenge in 2005 for the Mythbusters television show. Their initial small-scale test failed, leading them to initially declare the myth busted. However, undeterred, a student group from MIT later built a much more sophisticated apparatus using 127 square feet of mirror tiles. They successfully ignited a stationary wooden target in just over 10 minutes, proving that sustained ignition was achievable. Finally, in 2010, the Mythbusters team returned to the experiment with a new approach. Using 500 square feet of mirrors on a custom-built tracking mount, they managed to create a visible char and generate significant smoke on a ship's hull, though they did not achieve a sustained fire. They concluded that while incredibly difficult and perhaps not the most efficient weapon, the heat ray was not impossible, upgrading its status from busted to plausible. Whether Archimedes actually constructed and deployed such a device may never be proven conclusively by archaeology, but the more profound question it raises is not about historical fact, but about capability. The knowledge required to make it work, the principles of light reflection, the geometry of parabolic curves to create a focal point, and the understanding of solar energy as a concentrated heat source was absolutely within Archimedes' intellectual grasp. We know from his proven works that he had an extraordinary understanding of geometry and physics. He famously studied optics and wrote a lost treatise, Catoptrica, on the subject of mirrors. The idea of using shaped mirrors to focus light would not have been a magical leap for him. It would have been a natural application of his existing research. The real innovation would have been the engineering and deployment on such a massive, coordinated scale. This moves the story from the realm of pure myth into the territory of a brilliant thought experiment that could have been tested and may have even worked under ideal conditions. It illustrates a pattern we see again and again. The ancient world's brightest minds were not just theoreticians, they were applied scientists, constantly seeking ways to harness the fundamental forces of nature for practical purposes. They may not have had the formal laws of thermodynamics or a complete wave theory of light, but they understood the effects. They could see that curved, polished surfaces gathered light and heat, and in a moment of desperate conflict, the greatest mind of the age would have been the one to ask the obvious, brilliant question: if I can use a lever to move the world, why can't I use the sun to burn a fleet? While the legend of Archimedes' heat ray captures our imagination with its dramatic use of fire and light, the true testament to Roman engineering brilliance lies not in spectacular destruction, but in quiet, enduring creation. Walk through the streets of Rome today, and you can still touch structures that have stood for 2,000 years. The Pantheon, with its vast, unsupported concrete dome, still shelters visitors as it has since 128 of the Common Era. Roman harbors, like the one at Portus, remain partially submerged yet structurally sound after centuries of being pounded by saltwater waves. Modern concrete, by stark contrast, often begins to degrade within decades, requiring constant and costly maintenance. For a long time, we simply assumed the Romans had access to some mysteriously superior volcanic ash, a secret ingredient lost to time. But recent scientific breakthroughs have revealed a far more fascinating truth. Roman concrete wasn't just durable, it was, in a very real sense, alive. It possessed the almost magical ability to heal itself. The secret wasn't in a single, perfect recipe, but in a specific and seemingly flawed manufacturing technique that modern engineers would never have considered. The Romans made their concrete by mixing a volcanic ash called pozzolana with lime and water. The standard process involved first slaking the lime, mixing it with water to create a smooth, hydrated lime paste. This is how we make lime mortar today. But when researchers from MIT and other institutions used advanced scanning electron microscopy to examine pristine samples of ancient Roman concrete, they found something startling: tiny, distinctive bright white mineral chunks embedded throughout the material. These were millimeter-scale pieces of unreacted brittle quicklime, also known as calcium oxide. Their presence suggested the Romans had used a hot mixing method, combining dry, raw quicklime directly with the pozzolana and water. This would have created a highly exothermic, almost violent reaction, producing a much rougher, less homogeneous mix. To a modern materials scientist, this would look like a critical error. These unreacted lime inclusions are potential weak points, flaws that could initiate cracks. But the Romans, through generations of empirical trial and error, had discovered that these very flaws were the key to longevity. This is where the self-healing magic begins. As time passes, tiny, hairline cracks inevitably form in any concrete structure due to stress and weathering. In modern concrete, when water seeps into these microcracks, it's the beginning of the end. It carries in aggressive chemicals that corrode the steel rebar and expand upon freezing, widening the cracks until the structure fails. But in Roman concrete, that intruding water is not a destroyer, it's a trigger for repair. When water finds its way into a crack and encounters one of those bright white quicklime inclusions, a remarkable chemical sequence begins. The water reactivates the quicklime, dissolving it into a calcium-rich solution. This solution then flows into the crack where it comes into contact with the pozzolana in the surrounding concrete. A new reaction occurs, forming microscopic crystals of calcium carbonate, the same material as limestone, and additional cementitious compounds. These crystals grow, seamlessly filling and sealing the crack from the inside out, effectively healing the wound. It's a beautifully elegant, automatic repair system built directly into the fabric of the material itself. The profound implication is that the Romans were utilizing advanced chemical principles of mass transport and dissolution precipitation, reactions through pure practical observation. They had no periodic table, no understanding of atomic theory, and certainly no concept of the nanoscale crystallization processes they were orchestrating. They couldn't explain why hot mixed concrete with lime clasts performed better over centuries. They only knew from experience that it did. Their innovation was driven by the most practical of needs, building an empire that would last. They needed aqueducts that wouldn't crumble, harbors that could resist the relentless sea, and monumental structures that would proclaim the glory of Rome for generations. This practical pressure, combined with a culture of iterative engineering and a willingness to learn from both success and failure, led them to a formula that modern science is only now beginning to fully appreciate and attempt to replicate. Today, researchers are actively working on incorporating self-healing mechanisms into modern concrete, often using encapsulated polymers or bacteria. Yet the Roman model, using a cheap and abundant material like quicklime, remains one of the most promising and elegant solutions. Their 2,000-year-old concrete is more than just a building material. It is a silent, enduring lesson in humility. It reminds us that long-term resilience often requires thinking in cycles, not straight lines, and that sometimes the most advanced technology isn't about adding complexity, but about understanding and harnessing the simple, reactive nature of the world around us. The legendary blades known as Damascus steel represent one of history's most captivating examples of empirical mastery over materials. For over 1,000 years, from roughly the 3rd to the 17th century, swordsmiths in the Middle East, particularly in Syria, produced these weapons that were so revered they seemed to possess almost mythical qualities. What set them apart was a combination of properties that defied the limitations of ordinary steel. A true Damascus blade could take a razor's edge that would resist dulling even after fierce combat. It possessed a remarkable flexibility, allowing it to bend significantly without snapping, a life-saving feature on the battlefield. And most strikingly, its surface was etched with a mesmerizing, wavy pattern that resembled flowing water or swirling wood grain, a unique fingerprint that became the very symbol of its unparalleled quality. These swords were so prized that they were passed down through generations, and European crusaders returning from the Holy Land spoke of them in awe, describing their ability to slice through a silk scarf as it fell through the air or even cleave through another lesser sword. For centuries, the secret of how these blades were made was lost, a casualty of dying trade routes and guarded artisan traditions. The mystery only deepened in the modern era, as metallurgists trying to recreate the steel found themselves completely baffled. They could make strong steel and they could make flexible steel, but they couldn't make a single piece of metal that was both incredibly hard and astonishingly tough, all while displaying that characteristic watery pattern. It wasn't until the advent of powerful electron microscopes in the late 20th century that researchers were finally able to peer into the very atomic structure of surviving Damascus blades. What they discovered was nothing short of astonishing. Embedded within the steel were carbon nanotubes and cementite nanowires, structures of carbon arranged at the nanoscale that are at the very cutting edge of materials science today. These nanotubes, incredibly strong and lightweight cylindrical structures, and the reinforcing nanowires were the secret ingredients. They acted as a microscopic reinforcement, much like the rebar in concrete, giving the steel its unique combination of a hard, sharp edge and a flexible, shock-absorbing core. The presence of these nanostructures, created over 500 years before the term nanotechnology was even coined, is a staggering revelation. The process to create this wonder steel was a complex alchemy of art and precise, if unknowing, science. It began not with pure iron ore, but with small ingots of wootz steel, a type of high-carbon steel imported from India and Sri Lanka. These ingots already had a specific chemical signature containing trace impurities like vanadium, chromium, manganese, and most importantly, just the right amount of carbon. The master smith would then heat a puck of this wootz steel in a clay furnace, bringing it to a precise temperature where it was glowing a specific shade of yellow-orange, hot enough to be workable, but crucially, not so hot that it melted completely. They would then hammer it out, fold it, and weld it back together, repeating this process over and over. This wasn't just to create layers. Each cycle of heating and cooling, each precise hammer blow, was carefully manipulating the microstructure of the metal. The slow, controlled cooling process, often done in an insulated ash bed, was especially critical. It gave the carbon in the steel time to precipitate out and form those microscopic clusters of nanotubes and nanowires around the trace impurities, which acted as catalysts. The beautiful surface pattern wasn't merely etched on for decoration. It was a direct visual map of these underlying carbon clusters, revealed by polishing and etching the finished blade with acid. The true genius of the Damascus smiths was that they achieved this nano-engineering feat through sensory mastery and generations of accumulated craft knowledge, not theoretical understanding. They learned to read the colors of the heated steel to gauge temperature within a few crucial degrees. They learned to listen to the ring of the hammer to understand the metal's consistency. They learned through decades of trial and error that using ore from a specific mine, cooled at a specific rate, and folded a specific number of times, yielded a superior blade. They were effectively controlling variables at the nanoscale without any concept of atoms, molecules, or quantum mechanics. They weren't trying to create carbon nanotubes. They were simply trying to make the best possible sword, and through relentless empirical refinement, they stumbled upon a material technology that would not be formally discovered or intentionally replicated until the 21st century. The story of Damascus steel is ultimately a story of human intuition and dedication, a testament to how centuries of careful observation and a drive for perfection can lead to discoveries that seem to leapfrog across the ages, leaving behind artifacts that continue to mystify and inspire us. While the self-healing properties of Roman concrete represent a marvel of ancient material science, another structure on the opposite side of the world achieves a similar feat of defiance against time through an entirely different and perhaps even more mysterious process. Standing in the courtyard of the Qutb Minar complex in Delhi, India, is a towering iron pillar that has baffled scientists and historians for generations. For over 1,600 years, through scorching heat, drenching monsoon rains, and relentless humidity, this 23-foot-tall, 6-ton monument has refused to succumb to the most persistent enemy of iron, rust. While modern steel structures require constant painting and maintenance to fight off corrosion, often showing significant decay within mere decades, this ancient pillar remains smooth and largely uncorroded, a silent, stoic testament to a lost metallurgical art. Its very existence challenges our assumptions about the technological capabilities of ancient metalworkers. The secret to the pillar's longevity was not some magical, impervious alloy, but rather a beautifully complex and accidental form of self-preservation. Modern metallurgists, using tools like X-ray diffraction and electron microscopy, have discovered that the pillar protects itself with a thin, invisible barrier. This barrier is a crystalline layer of a compound called mesawite, a mixture of iron, oxygen, and hydrogen that forms a stable, protective film just microns thick on the surface of the metal. This film, known as a passive layer, is incredibly effective at shielding the iron beneath from the elements. It acts as a perfect shield, preventing water and oxygen from reaching the pure metal and initiating the destructive electrochemical reactions we know as rust. This process, called passivation, is a cornerstone of modern metallurgy. We intentionally use it today when we add chromium to steel to create stainless steel, which forms a similar protective chromium oxide layer. The astonishing fact is that the creators of the Delhi pillar achieved this same effect over 15 centuries ago, not through intentional alloying, but through the unique chemical signature of their iron. This incredible accident was born from the specific methods used by ancient Indian smiths, known as the Dhaka technique. They did not smelt iron in massive blast furnaces as we do today. Instead, they used small, clay-lined furnaces called crucibles, where they would heat iron ore with charcoal. This process resulted in a solid, high-phosphorus wrought iron bloom, not molten metal. The high phosphorus content is the first critical piece of the puzzle. The ore and charcoal available to them naturally contained significant amounts of phosphorus, which became incorporated into the iron during the smelting process. This was not a deliberate addition. It was simply an impurity inherent to their local materials and process. The second critical step was their forging technique. The hot iron was hammered and worked over time, folding and welding it to squeeze out slag and consolidate the metal. This mechanical working, combined with the high phosphorus, created a unique microstructure. Here is where the ancient empiricism truly shines. The Indian metalworkers had no knowledge of electrochemistry, oxidation states, or passivation phenomena. What they did have was generations of accumulated, hands-on knowledge. They learned through trial and error that iron produced with their local materials, when worked in a specific way, resulted in a superior metal that lasted longer. They could observe the performance of their products over time. They would have seen that tools, weapons, and pillars made from this particular iron did not corrode as quickly as others. They perfected a craft that consistently produced this result, all while remaining completely unaware of the nanoscale chemical magic they were orchestrating. The high phosphorus content in the iron prevents the formation of the usual non-protective rust. Instead, when the surface is exposed to the atmosphere, it reacts with moisture and air to slowly build that uniform, adherent mesawite film. The initial exposure did cause a very slight amount of corrosion, but that corrosion product itself became the ultimate protector. The pillar, in essence, created its own perfect, perpetual rust jacket. The Delhi iron pillar is more than just a curious artifact. It is a profound lesson in the power of optimized process over theoretical understanding. Its creators were not alchemists trying to invent stainless steel. They were master craftsmen refining their art to its practical peak. They manipulated variables they could control: the choice of ore, the type of charcoal, the heating temperature, and the rhythm of the hammer, to achieve a desired outcome they could observe: strength and durability. In doing so, they stumbled upon a principle of materials science that would remain a mystery until the 20th century, when scientists like Carl Wagner and Ulrich R. Evans began to formally unravel the electrochemical theory of corrosion and passivation. The pillar stands today not as a monument to a forgotten king whose inscription it bears, but as a monument to human ingenuity itself. It reminds us that deep, systematic observation of the natural world can yield solutions so advanced that their underlying logic remains hidden for millennia, waiting for future generations to finally discover the science behind the craft. From the precision-forged metals of Damascus and Delhi, we now journey to the arid plains of southern Peru, where an entire civilization chose the earth itself as its canvas, creating an art so vast it can only be comprehended from the heavens. Etched into the dark, rocky surface of the Nazca Desert over a 1,000-year period between 500 years before the Common Era and 500 years after, lies one of archaeology's most breathtaking and enigmatic spectacles, the Nazca Lines. These are not mere scratches on the ground, they are geoglyphs of monumental scale and staggering complexity. Imagine a hummingbird, its wingspan stretching over 250 feet, drawn with a single, unbroken line. Picture a condor with a 400-foot wingspan, a spider nearly 150 feet across, and a monkey with an intricately coiled tail. Alongside these biomorphic figures are geometric marvels, trapezoids that stretch for hundreds of yards, triangles pointing to distant mountains, and lines, over 800 straight lines, some of which run perfectly straight for miles across the uneven desert floor, defying the curvature of the earth itself. The sheer act of creating these designs is a monumental puzzle. The Nazca people, without the wheel, without draft animals, and without any written language that we can decipher, achieved a feat of precision engineering that would challenge modern surveyors. Their method was one of brilliant simplicity. The desert pavement is covered in a layer of dark, iron oxide-rich pebbles. By removing these top stones to reveal the lighter, sandy soil beneath, the artists created high-contrast lines. But the real genius was in the execution. Researchers like Maria Reich, who dedicated her life to studying the lines, proposed that the Nazca used a system of scaled models and simple surveying tools. A small-scale drawing could have been laid out on a grid, with stakes and ropes used to transcribe the design to a massive scale on the desert floor. To create their impossibly straight lines stretching to the horizon, they likely used a series of sighting posts. By aligning two or more stakes, they could maintain a straight course for kilometers, visually correcting for any slight deviations as they went. This method required no advanced mathematics, no theorems, just a profound understanding of practical geometry and an artist's eye for proportion and scale. This leads us to the captivating and enduring mystery. Why? What compelled a people to undertake such a gargantuan effort, creating art they could never fully see? The theories are as vast and varied as the lines themselves. One of the earliest and most persistent ideas, championed by Reich, is that the lines formed a massive astronomical calendar. Certain lines do align with the solstice sun, and some animal figures may correlate with constellations as the Nazca saw them. The desert floor could have been a celestial map used to mark changing seasons and important dates for their agriculture. Another compelling theory views the geoglyphs as sacred pathways for ritual processions. In this view, the act of walking the lines, the spider's leg, the monkey's tail, the long trapezoids was a form of spiritual pilgrimage, a walking meditation that connected the people to the deities these figures represented. The lines might have been used only once for a specific ceremony, which would explain the lack of erosion or paths worn by frequent use. A more recent and fascinating hypothesis suggests a connection to water, the most precious resource in the desert. The geoglyphs are located above a complex underground aquifer, and many of the lines point directly toward distant water sources in the mountains. The animal figures, like the hummingbird or the monkey, are often associated with water and fertility in Andean mythology. The creations may have been a desperate and beautiful prayer to the gods, a massive ceremonial offering to ensure the life-giving flow of water. Perhaps the most profound aspect of the Nazca lines is not any single theory, but what their existence tells us about the human capacity for abstract thought and spatial reasoning. The Nazca people demonstrated a masterful ability to conceptualize and execute massive, two-dimensional designs in a three-dimensional landscape. They understood perspective and scale in a purely practical way, manipulating their environment to create coherent forms that only make sense from an elevated, God's-eye view. This suggests a mind capable of holding complex spatial relationships and translating them into physical reality through empirical, hands-on methods. They didn't need Euclid's formal geometry or Cartesian coordinates. They developed their own system of measurement and alignment that was perfectly suited to their needs and their world. The lines stand as a testament to a different kind of knowledge, one that is embodied, practical, and deeply connected to the environment. They are a permanent record of a people who looked at a vast, empty desert and saw not a wasteland, but a canvas for their beliefs, their science, and their art, leaving behind a mystery that continues to draw us upward, urging us to look down from the sky and wonder. While the monumental geoglyphs of Nazca demonstrate a mastery of space and alignment, the ancient Greeks were perfecting the measurement of something even more elusive, time itself. In the bustling agoras and solemn courts of ancient Greece, the flow of water became the heartbeat of civic life, measured out by ingenious devices known as Klepsydra or water thieves. These were not mere buckets with holes, but sophisticated instruments of remarkable precision, designed to solve a fundamental human problem: how to fairly and accurately portion out the most finite resource of all. Imagine an Athenian courtroom where a lawyer's entire case might be limited to the time it took for a specific amount of water to drain from a vessel. The Klepsydra ensured that each speaker had an equal and unbiased allotment, its steady drip creating a level playing field long before the invention of the mechanical stopwatch. This practical need for fairness in legal and political proceedings was the primary engine driving the water clock's development from a simple pot into a marvel of hydraulic engineering. The simplest water clocks operated on an elegantly straightforward principle. A ceramic vessel with a small, carefully drilled hole near its base would be filled with water. As this water steadily drained out, its falling level would indicate the passage of time against marks inscribed on the vessel's interior. But the ancient engineers quickly encountered a fundamental physical problem: the flow isn't constant. As the water level in the vessel drops, the water pressure at the outlet decreases, causing the flow to slow down. A clock that ran fast when full and slow when nearly empty was useless for any serious timekeeping. The Greek solution to this was a masterpiece of empirical innovation. Instead of a single outflow vessel, they developed an inflow design. A constant stream of water would drip into a receiving container, and the rising water level inside this second vessel would indicate the time on a calibrated scale. To maintain a truly constant inflow rate, they ensured the supply reservoir was kept at a perfectly steady level, often by using a third overflow tank. This clever arrangement automatically compensated for the variable flow, harnessing the principle of communicating vessels to create a steady, predictable trickle. They had, in effect, invented a constant flow regulator centuries before the physics of hydrostatics would explain why it worked. This drive for accuracy led to increasingly complex and breathtaking mechanisms. The greatest example of this evolution is the horologion of Andronikos of Chios, also known as the Tower of the Winds in Athens. This magnificent octagonal tower, built in the 1st century before the Common Era, housed a massive and intricate water clock that was far more than a simple timer. Its water flow was regulated by a complex system that powered an entire array of displays. It likely featured rotating dials to show the hour, and some accounts suggest it included moving models of the planets and indicators for important astronomical events. This wasn't just a clock, it was a planetarium, a public monument to Greek ingenuity that used the relentless force of flowing water to model the heavens themselves. The gears and mechanisms within represent a direct conceptual ancestor to the Antikythera mechanism, proving that the Greek mastery of hydraulics and gearing was a sophisticated and widespread tradition. Every component of these advanced Klepsydra was an application of physical principles that would remain formally unstated for over 1,000 years. The steady flow from the supply reservoir demonstrated an intuitive grasp of the relationship between hydraulic head and pressure, the core of what would become Bernoulli's principle. The use of narrow, precisely drilled outlets showed an understanding of viscosity and laminar flow, concepts that would only be mathematized by scientists like Euler and Navier in the 18th and 19th centuries. The Greek engineers had no equations for fluid dynamics. They had observation, experimentation, and a relentless practical need. They learned through trial and error that a longer, narrower tube produced a more consistent flow than a short, wide hole. They discovered that certain shapes of vessels minimized turbulence and splashing. They were manipulating variables to achieve a desired outcome, mastering the effects of fluid mechanics long before they could describe the causes. The water clock stands as a powerful symbol of this entire era of invention, a device born from the democratic need for fairness, refined by the scientific desire for accuracy, and perfected through a hands-on understanding of the natural world that was, in its own way, as profound as any theoretical formula. Moving from the steady drip of Greek water clocks, we venture into ancient China, where engineers achieved a different kind of precision, not in measuring time, but in defying disorientation. During the tumultuous era of the Three Kingdoms, around the 3rd century of the Common Era, a legendary inventor and mechanical engineer named Ma Jun created a device so bafflingly clever it seemed to possess a mind of its own. This was the south-pointing chariot, an elaborate carriage-mounted figure that would perform a miracle every time the vehicle turned. Its outstretched arm would continuously pivot, always unfailingly pointing toward the south. In an age long before the magnetic compass was commonplace for navigation, this mechanical marvel provided a constant, reliable cardinal direction, no matter how winding or complex the path traveled. It was, in essence, a robotic navigator, a piece of analog artificial intelligence built from wood and bronze. The internal mechanism was a masterpiece of mechanical feedback, a system so advanced it would not be formally understood for 1,700 years. At its heart was a differential gear assembly, a complex set of interlocking gears that allowed two different inputs to be compared and a single output to be adjusted accordingly. Here is how this mechanical ballet worked. As the chariot moved forward in a straight line, the gears remained in equilibrium and the figure pointed true south. But the moment the chariot began to turn, the system detected the change. The wheels were connected to the gears, but the two wheels would rotate at different speeds during a turn. The outside wheel would cover more ground than the inside one. This difference in rotational speed between the left and right wheels was the critical input. The differential gears would sense this imbalance and, through a beautiful series of mechanical calculations, would drive the figure on top to rotate in the exact opposite direction of the chariot's turn and at precisely the same rate. If the chariot turned 90 degrees to the east, the figure would rotate 90 degrees to the west, perfectly counteracting the motion and maintaining its southern bearing. It was a closed-loop control system, automatically correcting for error without any human intervention. The profound genius of this device lies in the principles it unknowingly employed. The Chariot's mechanism was a physical embodiment of what 20th century scientists would term a negative feedback loop, the foundational concept of cybernetics. This is the same principle that allows a modern thermostat to maintain a room's temperature or a cruise control system to maintain a car's speed. The system constantly monitors its output, the direction the figure is pointing, compares it to a set goal true south, and makes continuous adjustments to minimize the error. The Chinese engineers had no theory of control systems, no block diagrams, and no mathematical models of feedback. Their understanding was entirely kinematic. They knew that if they connected gear A to wheel B in a specific way, the result would be a specific, predictable, and useful motion. They translated an abstract navigational problem into a tangible mechanical solution. It was engineering through pure geometry and motion, a physical algorithm carved in bronze. This creation was more than just a clever toy. It held deep cultural and strategic significance. In Chinese cosmology, south was the most auspicious direction, associated with the emperor and warmth. On the practical battlefield, such a device would have been an invaluable tool for generals moving large armies through featureless terrain or under cloud-covered skies where the sun and stars were hidden. It provided a constant, unchanging reference point, allowing for coordinated troop movements and preventing disorientation in the fog of war. The south-pointing chariot stands as a stunning example of how a pressing practical need can inspire technological solutions that seem to leapfrog through time. It demonstrates that the core concepts of automation and control ideas we associate with the digital age were not only conceivable but were actually being built and used in the ancient world, achieved not with electronics or code, but with the sublime interplay of gear, teeth, and human ingenuity. While the Chinese south-pointing chariot solved the problem of terrestrial navigation through mechanical genius, the ancient Maya were looking far beyond the horizon, turning their gaze upward to map the cosmos itself with a precision that would not be matched in Europe for centuries. In the dense rainforests of Mesoamerica, far from the philosophical schools of Greece or the imperial courts of China, Maya astronomer priests constructed a breathtakingly accurate model of time and celestial motion, all without telescopes, without written numbers as we know them, and without any underlying theory of gravity or planetary mechanics. Their tools were not made of bronze gears, but of keen observation, relentless record-keeping, and a complex mathematical system that saw time not as a simple linear progression, but as a series of interlocking, sacred cycles. For the Maya, astronomy was not an abstract pursuit. It was the very language of the gods, a way to divine the will of the deities who controlled the rains, the harvests, and the fate of their civilization. This profound spiritual need drove them to achieve a level of observational accuracy that remains stunning today. The crown jewel of their astronomical achievement is undoubtedly the Venus table found within the Dresden Codex, one of the few surviving pre-Columbian Maya books. This intricate chart tracks the movements of Venus across a span of nearly 484 years, predicting its appearances as the morning and evening star with an error margin of just 1 day in 6,000 years. To put that in perspective, this means their predictive model would have been accurate to within a single day for a period longer than the entire span of recorded human history since the invention of writing. This wasn't a lucky guess. It was the result of generations of unbroken observation, with priest astronomers meticulously recording the planet's position night after night, century after century. They were tracking the planet's synodic period, the 584 days it takes for Venus to return to the same position relative to the Sun and Earth as seen from our planet. They understood that this cycle was not perfect, that it contained slight irregularities, and they built corrective factors into their calculations to account for these tiny drifts over immense stretches of time. They achieved this not by understanding why Venus moved as it did. They had no concept of heliocentric orbits or elliptical paths, but by discerning the intricate pattern of its motion through the sky and creating a mathematical framework to replicate it. Their methodology was a masterclass in empirical science. They built specialized observatories like the Caracol at Chichen Itza, a unique tower-like structure with narrow window slits aligned to capture the extreme positions of Venus on the horizon. They used cross sticks similar to a surveyor's tool to measure precise angles against the horizon. Every observation was carefully recorded in their complex calendar system, which itself was a marvel of timekeeping, interweaving a 260-day sacred calendar with a 365-day solar year. This allowed them to see how celestial events correlated with earthly ones, believing that the past held the key to the future. If a war had been lost when Venus appeared in a certain phase, they might delay a battle when that phase recurred. Their astronomy was deeply predictive and deeply practical, woven into the very fabric of their political and religious decision-making. The true wonder of Mayan astronomy lies in this disconnect between their phenomenal results and their complete lack of a theoretical framework for why the heavens behaved as they did. They had no Newtonian laws of gravitation, no Keplerian ellipses, and no concept of a physical force governing planetary motion. Theirs was a universe animated by deities. The sun was a god carried on a litter through the underworld at night, and Venus was the fearsome god Kukulkan, whose different phases signaled omens of war or fortune. Yet, by treating the cosmos as a giant, divine clockwork and dedicating themselves to recording its every tick and tock, they managed to reverse engineer its mechanics with stunning accuracy. They didn't need to know about gravitational constants or orbital velocities. They discovered that the universe was predictable through pattern recognition on a grand scale. This demonstrates a powerful truth about human discovery, that intense, systematic observation can yield incredibly sophisticated models of natural phenomena, long before we develop the scientific theories that explain the underlying causes. The Maya looked up, saw a pattern, and trusted the pattern completely, building a civilization's worldview on the precise, predictable dance of the planets. While the Maya were mapping the heavens through meticulous observation, Persian architects were mastering a far more earthly challenge: how to live comfortably in one of the most punishing climates on Earth. In the scorching, arid plains of central Iran, where summer temperatures can soar well above 110 degrees Fahrenheit, they developed an architectural marvel that provided relief centuries before the invention of electric air conditioning. These structures, known as wind catchers or badgers, rise from the rooftops of ancient cities like Yazd and Kashan like elegant rectangular towers, silently channeling the breath of the wind into the homes and public buildings below. Their design is deceptively simple: a tall, capped tower with openings facing the prevailing wind, connected to the main living quarters by a vertical shaft. But within this simplicity lies a profound understanding of the natural world, a way to manipulate the very air itself to create cool, habitable spaces in the heart of the desert. The operation of a wind catcher is a beautiful dance of physics, harnessing two separate natural phenomena to achieve its cooling effect. The first method captures even the faintest breeze. The tower's openings are strategically oriented to face the most reliable wind direction for that region. As the wind blows against the tower, it is funneled downward through the shaft, creating a direct breeze that ventilates the interior rooms. But the true genius is revealed on completely still, windless days when the air is heavy and stagnant. This is where the second, more subtle mechanism takes over. The wind catcher transforms into a passive cooling engine driven by temperature differences. The interior of the building, particularly any adjacent underground rooms or water sources like a canat, an underground canal, remains significantly cooler than the sun-baked rooftop. Hot air inside the building, being lighter, naturally rises. This rising air creates a pressure difference, effectively sucking the cooler, denser air from the basement or courtyard up through the living space and out through the wind catcher tower. The tower itself, heated by the sun, further accelerates this process by causing the air within it to heat up and rise even faster, pulling a continuous stream of cool air through the home in a silent, self-sustaining cycle. What is truly humbling about this technology is that its creators were manipulating principles of fluid dynamics and thermodynamics that would not be formally described by scientists for over a millennium. The wind catcher's ability to capture wind relies on converting the kinetic energy of moving air into a pressure gradient that forces it down a shaft, a practical application of what would become Bernoulli's principle. The passive stack ventilation, driven by the difference in air density between hot and cold areas, is a masterful use of convection currents and the ideal gas law, concepts that would be cornerstones of thermodynamics. The Persian architects had no equations for these forces. Their knowledge was entirely empirical, born from centuries of observing how air moved and how heat behaved. They learned through trial and error that a taller tower created a stronger draft, that certain shapes and orientations captured the wind more efficiently, and that coupling the tower with a cool source like a basement or water reservoir dramatically enhanced the cooling effect. They were intuitive physicists designing systems that worked in harmony with nature's laws long before those laws had names. The impact of this technology on daily life cannot be overstated. It allowed for the development of dense urban centers in otherwise uninhabitable regions. Large wind catchers were built over public cisterns to keep drinking water cool. Elaborate systems were integrated into grand bazaars, caravanserais, and homes, creating comfortable environments for commerce, travel, and family life. The design was so effective that it spread across the Middle East and North Africa, evolving into various forms like the Malkaf in Egypt. In an era of increasing energy consumption and concerns about sustainability, the ancient wind catcher stands as a powerful testament to the potential of passive bioclimatic architecture. It requires zero electricity, produces no emissions, and uses a renewable resource, the wind, and the natural temperature differential between day and night. It represents a pinnacle of green design, achieved not through complex technology, but through a deep, observant, and respectful dialogue with the local environment. It is a timeless reminder that some of the most advanced solutions are those that work with nature, rather than seeking to overpower it. Rising from the sands of Egypt like petrified rays of the sun, the mighty obelisks were far more than just symbols of pharaonic power. They were the very clockwork of the civilization, stone giants that transformed sunlight into a measurable, predictable flow of time. These towering monoliths, some weighing over 400 tons and reaching heights of nearly 100 feet, were precisely quarried from a single block of red granite, transported down the Nile on colossal barges, and erected with an engineering prowess that still inspires awe. But their true purpose extended far beyond mere spectacle. Their four sides, meticulously aligned with the cardinal directions, and their pyramid-shaped apexes, often sheathed in electrum to catch the first and last light of the day, were all carefully designed components of a grand, open-air astronomical instrument. The ancient Egyptians didn't just build these structures to impress. They built them to observe, to calculate, and to harmonize their entire society with the relentless cycles of the cosmos. The most straightforward function of an obelisk was that of a giant gnomon, the pointer of a sundial on a monumental scale. As the sun journeyed across the sky, the obelisk would cast a sweeping shadow that moved in a predictable arc across the surrounding plaza. Markings on the ground, now largely lost to time, likely allowed priests to divide the day into hours by tracking the shadow's tip. The length and direction of this shadow told a complex story. At noon, when the sun reached its highest point, the shadow would be at its shortest, marking the midpoint of the day. The variations in the shadow's path from summer to winter also served as a precise solar calendar. During the summer solstice, when the sun is at its highest peak in the sky, the noon shadow would be at its absolute shortest. Conversely, at the winter solstice, the low-hanging sun would cast the longest shadow of the year. By monitoring these extreme points, Egyptian astronomers could accurately determine the length of the solar year and mark the critical turning points for agriculture, such as the imminent arrival of the Nile's annual flood. This practical application reveals a deep, empirical understanding of solar geometry that wouldn't be formally described for millennia. The Egyptians had no concept of the Earth's axial tilt of approximately 23.5 degrees, which is the actual cause of the seasons and the variation in the sun's altitude. They didn't need this theoretical knowledge. Through generations of patient observation, they had perfectly mapped the sun's changing path and its effects. They knew what happened with exquisite precision, even if they didn't know the abstract why. This knowledge was encoded directly into their architecture. The precise orientation of temple complexes often involved aligning an obelisk so that on a specific holy day, like the king's coronation anniversary or a religious festival, its shadow would fall directly upon the inner sanctum's altar or touch the statue of a god. This transformed a celestial event into a powerful terrestrial ritual, literally bringing the power of the sun god Ra into the heart of their worship. The legacy of the obelisk's timekeeping function is etched into our very language. The word itself comes from the Greek obeliskos, meaning little spit, a reference to its pointed shape. But a more profound inheritance is the ancient Egyptian symbol for a unit of time, which was a small, simplified hieroglyph of an obelisk. This direct link between the object and the concept of time itself underscores its fundamental role in their worldview. Furthermore, the obelisk's journey from Egypt to the squares of Rome, Istanbul, London, and New York is a story of imperial trophy hunting, but it also created a fascinating historical irony. When these plundered monuments were re-erected in new northern latitudes, their shadows began tracing entirely different, unfamiliar paths. The carefully calibrated relationship between the stone and the sun was broken, transforming these precise scientific instruments into purely decorative symbols, their original function silently forgotten in their new homes. They stand today as majestic mysteries to most who pass by, their true purpose as sophisticated solar calculators waiting to be rediscovered by those who know how to read the language of light and shadow. High in the Andes Mountains, where the very earth itself is alive and constantly shifting, the Inca civilization faced a relentless architectural adversary, devastating earthquakes. Rather than trying to defeat this immense, unpredictable force, their master builders chose a path of brilliant humility. They learned to dance with it. The result is some of the most enduring and enigmatic masonry the world has ever seen. At sites like Machu Picchu and Sacsayhuaman, we find walls composed of massive, irregularly shaped stones, some weighing over 100 tons, carved and polished to fit together with a precision that seems to defy the tools of the age. The joints are so tight that even today you cannot slide a razor blade between them. This perfection was not merely for aesthetic showmanship, it was the very heart of a sophisticated seismic defense system, engineered through centuries of observing how the Earth moves. The genius of Inca stonework lies in its dynamic flexibility, a concept completely at odds with the rigid, monolithic structures of later European design. Instead of building walls that were perfectly vertical, the Incas intentionally constructed them with a slight inward incline and a subtle convex bulge. This curvature gives the entire structure a lower center of gravity, making it far more stable when the ground begins to heave, but the true marvel is in the joints themselves. Each stone is a unique puzzle piece with multiple interlocking facets and often tapered sides that wedge it firmly against its neighbors. Unlike a mortared wall, which is brittle and acts as a single, rigid unit, an Inca wall is a complex matrix of individual blocks. When seismic waves roll through the foundation, this matrix comes alive. The stones in the wall, what engineers call ashlars, are permitted to vibrate and shift minutely against one another. This movement dissipates the terrifying energy of the earthquake across the entire structure, allowing it to be absorbed and redirected. The wall literally dances, swaying and settling as the quake passes, and then, almost miraculously, the stones fall back into their original positions, locked in place once more by gravity and their perfect fit. It is a brilliant example of what modern engineering calls energy dissipation through controlled deformation. This architectural philosophy represents a profound understanding of structural dynamics that wouldn't be formally codified until the 20th century. Today, engineers use base isolators and tuned mass dampers in skyscrapers to achieve a similar effect, allowing a building to move independently of its shaking foundation. The Incas, through pure empirical observation, developed their own version of this principle. They had no theory of plate tectonics, no equations for wave propagation, and no concept of harmonic resonance. What they did have was a long memory and a keen eye. They observed which types of structures collapsed in a quake and which ones remained standing. They noticed that rigid, brittle constructions shattered, while more flexible, jointed assemblies often survived. Through generations of trial and error, they refined their stone-cutting techniques to create the ultimate anti-seismic building block. Their method was a form of applied Darwinian engineering. The designs that survived the test of earthquakes were the ones replicated and perfected. This approach stands in stark contrast to the later Spanish conquistadors, who built their colonial churches and administration buildings directly on top of Inca foundations using rigid, mortared brick and stone. Time and again, when a major earthquake strikes the region, the result is the same. The Spanish upper structures crumble into rubble, while the flawless Inca foundations beneath them remain steadfast and unshaken. This visible testament to their ingenuity is perhaps the most powerful evidence of its effectiveness. The Inca builders were not just stacking rocks, they were encoding the lessons of countless seismic events into their very architecture. They understood that to resist an earthquake, you must not fight its energy, but rather you must invite it in, allow it to move through your structure, and then gently show it the way out. For a long time, the Antikythera mechanism was considered a glorious anomaly, a single, inexplicable spark of genius that somehow flashed in the ancient world and was then lost for 2 millennia. But what if it wasn't an anomaly at all? What if it was simply the most spectacular survivor of a much broader tradition of ancient Greek mechanical computation? A growing body of evidence, pieced together from scattered literary references and archaeological clues, suggests that the device found in that shipwreck was far from unique. It may have been one of the finest examples of a known class of instruments, a peak within a whole mountain range of technological achievement that has since been eroded by time. The most compelling hints come from the writings of ancient authors who casually mention devices that sound astonishingly similar. Cicero, the Roman orator and philosopher, describes a device built by his friend Posidonius in the 1st century before the Common Era that replicated the movements of the Sun, Moon, and 5 known planets. He calls it a sphera, a sphere, and notes that its rotating motions showed the same eclipses of the Moon and Sun as happen in the heavens. Even more intriguingly, he references an earlier planetarium model constructed by the great Archimedes himself, which was captured as war booty when the Roman general Marcellus sacked Syracuse. Marcellus, Cicero writes, took this single device as his personal prize, a testament to its incredible value and complexity. Archimedes, a mind centuries ahead of his time, had apparently written a lost treatise, now known only by its title, on sphere making, which likely detailed the construction of such mechanical orreries. These were not simple models, they were functional analog machines designed to simulate the cosmos. The philosophical implications of these devices were as profound as their mechanical ones. In a world where the motions of the heavens were considered divine and eternal, the idea that a human-made machine of gears and cogs could physically replicate and predict those motions was revolutionary. It suggested a universe that operated on regular, predictable principles, a clockwork cosmos. This mechanical worldview, which wouldn't fully take hold in Europe until the time of Newton and Leibniz, was being physically modeled by Greek engineers through bronze and hand-cranked power. The very existence of these machines pushed the boundaries of thought, forcing a reconciliation between the divine, unpredictable will of the gods and the precise, predictable turning of a geared mechanism. They were not just calculators, they were philosophical statements made of metal. The concept at the heart of these inventions is what we now call analog computation. Unlike a digital computer which breaks down problems into binary bits of ones and zeros, an analog computer uses continuous physical phenomena to model the problem itself. In the case of the Antikythera mechanism, the rotation of a hand crank represented the flow of time. The turning of specific gear trains with their carefully calculated ratios physically represented the orbital periods of the Moon and planets. A gear with 63 teeth might interact with another to model the Moon's subtle variations in speed. The machine didn't calculate an answer in the abstract. It physically manifested the answer through its own state. To ask about the position of Venus in 50 years, you would simply turn the crank the corresponding number of times and read the result directly from the dial. The machine was the calculation. This approach reveals a different cognitive path to understanding the universe. The Greeks of this era were brilliant geometers and logicians, but their theoretical physics was not yet fully developed. They didn't have the Newtonian laws of motion or universal gravitation to explain why the planets moved as they did. However, they had meticulously observed how they moved. They had derived the precise mathematical ratios of their cycles. The fact that Venus goes around the Sun 13 times for every 8 times Earth does. Their genius was in realizing they could translate these pure mathematical ratios, these abstract numbers, into physical form. They could embody the mathematics in a tangible machine. A gear train is, at its core, a physical expression of a mathematical ratio. By building a mechanism that perfectly mirrored the celestial ratios they had observed, they could simulate the heavens without needing to first derive the underlying laws of physics. They built the model first and understood the theory later. The tragic loss of this technological tradition is one of history's great what-if scenarios. The knowledge required to build these devices, precision metalworking, advanced gear design, and deep astronomical understanding, was likely concentrated in a few great centers of learning like Alexandria, Rhodes, and Syracuse. As these centers declined due to war, political instability, and ultimately the collapse of the Roman Empire, the highly specialized craft of building complex, geared mechanisms seems to have faded away. The knowledge was too fragile, too dependent on a stable, scholarly environment and a chain of master artisans passing down their secrets. The world entered a long period where such devices were unimaginable. When mechanical clocks with complex gear trains finally reappeared in medieval Europe, they were celebrated as unprecedented marvels, their inventors completely unaware that they were, in fact, reinventing a technology that had been mastered over 1,000 years earlier. The story of Greek analog computers is a powerful reminder that progress is not always a straight line, and that great leaps forward can be lost, waiting patiently in the silt at the bottom of the sea for us to rediscover them. While the Greeks and Byzantines were forging their mechanical legacies on the other side of the world, in 11th century China, an engineer and statesman named Su Song was commissioned to solve a problem of celestial timing that had embarrassed the imperial court. The existing calendars and clocks had fallen out of sync with the heavens, leading to errors in predicting eclipses and scheduling crucial rituals. Su Song's response was not merely a new timepiece. It was a monumental, multi-story tower of mechanical wonder that stood over 30 feet tall, known as the water-powered armillary sphere and celestial globe. This was not a device hidden away in a scholar's study. It was a public marvel, a cathedral of precision engineering designed to showcase the emperor's mandate to harmonize human affairs with the cosmos itself. At the very heart of this colossal machine was its most revolutionary feature, a water-driven escapement mechanism. This was the crucial innovation that transformed the clock from a simple water clock into a regulated, mechanical marvel. The escapement's job was to take the relentless, continuous flow of water and break it down into precise, measured, discrete units of time. Here's how it worked. Water would steadily drip into a series of scoops on a large water wheel. Once the weight of the water in a scoop reached a critical point, it would trip a lever. This lever would release a brake, allowing the wheel to rotate just one step forward before the brake instantly locked it in place again. This cycle of catch and release happened with a rhythmic, ticking regularity, converting the smooth flow of a liquid into the steady, punctuated beat that is the foundation of all mechanical timekeeping. This invention, which Su Song documented in intricate detail in his book Xin Yi Zhang Fa Yao, was a mechanical concept of such profound importance that it would not appear in European clockmaking for another 200 years. This regulated pulse of power was then transmitted through a complex forest of gears and driveshafts to animate the clock's breathtaking displays. At the top of the tower, a bronze armillary sphere, a skeletal model of the celestial sphere, rotated automatically, its rings tracing the paths of the stars and planets. Inside the tower, a celestial globe, also turning in sync, provided a map of the heavens for scholars to study. But perhaps the most publicly engaging feature was the procession of automated figurines that emerged from behind carved doors at the top of each hour. Little mechanical puppets would ring bells, beat drums, and hold up tablets to announce the time, a dazzling spectacle of automation that brought the abstract mathematics of astronomy into a vibrant, theatrical performance for all to see. The sheer ambition of synchronizing all these components, the armillary sphere for observation, the globe for calculation, and the timekeeping displays for public use, reveals a systems engineering mindset that was staggeringly advanced. Su Song and his team were integrating mechanics, hydraulics, and astronomy into a single, cohesive unit. They were grappling with concepts of energy transfer, load management, and precision control that wouldn't be formally analyzed until the rise of European mechanical engineering during the Renaissance. They had no formal theory of gear ratios or torque. Instead, they worked from practical principles, understanding through calculation and experimentation that a specific sized gear with a certain number of teeth would produce a desired rotational speed to match a known astronomical cycle. This clock tower stands as the ultimate expression of a long and sophisticated Chinese tradition of astronomical instrumentation. It was the culmination of centuries of development, building upon the work of earlier masters like Zhang Heng and Yi Xing. It represents a path of technological progress that was deeply intertwined with the state's philosophical and bureaucratic needs. The accurate calendar was essential for governance, agriculture, and affirming the emperor's cosmic authority. This practical, state-sponsored drive for precision, combined with a culture that valued meticulous record-keeping and empirical observation, created an environment where such a mechanical masterpiece could be envisioned and built. Zhu Song's clock was more than a machine. It was a physical manifestation of a worldview, a towering testament to the idea that the orderly principles of the heavens could be understood, measured, and replicated here on Earth through the sublime language of gears, water, and bronze. As the mechanical clocks of Zhu Song's China marked the hours with automated figures, a parallel revolution in programmed movement was unfolding thousands of miles to the west in the vibrant intellectual capitals of the Islamic world. During the Golden Age of Islam, from the 8th to the 14th centuries, a unique fusion of inherited knowledge and bold innovation gave rise to a tradition of engineering that seemed to breathe life into inanimate matter. In the courts of caliphs and sultans, legendary inventors like the Banu Musa brothers and Al-Jazari designed and built astonishing machines that were not merely tools but performers, servants, and entertainers. These weren't simple novelties, they were complex automata, programmable machines that could carry out intricate sequences of actions, captivating audiences and serving practical purposes with a level of sophistication that would not be seen again in the West for hundreds of years. The sheer variety of these creations reads like a catalogue from a steampunk fantasy. Imagine a grand banquet where a life-sized humanoid automaton, a graceful waiter, would emerge from a hidden cabinet to refill the guests' cups. This mechanical servant, described in Al-Jazari's Book of Knowledge of Ingenious Mechanical Devices, would float across the room on a boat-shaped platform hidden within a lake of mercury, its movements smooth and silent. Upon reaching a guest, it would bow, extend its arm, and pour a precise measure of drink before returning to its station, all driven by a complex system of weights, pulleys, and water clocks. In another corner of the palace, a magnificent water-powered peacock might slowly rotate, fanning its elaborate tail feathers in a mesmerizing display of hydraulic artistry. Elsewhere, programmable musical instruments could play different melodies automatically, their notes plucked or drummed by tiny mechanical fingers controlled by a rotating cylinder studded with pegs, a direct ancestor to the music box and the programmable loom. These spectacles were more than just royal entertainment. They were powerful demonstrations of a ruler's wealth, wisdom, and command over both the natural and mechanical worlds. The magic behind these illusions was a toolkit of advanced mechanical principles, all achieved without a single line of code or a theory of control systems. Primary innovation was the sophisticated use of cams. A cam is an irregularly shaped wheel or lobe mounted on a rotating shaft. As the shaft turns, the cam's unique profile pushes against a follower, a lever or rod, converting simple rotational motion into any desired pattern of linear or oscillating movement. By carefully designing the shape of a cam, an engineer could dictate exactly when and how a lever would lift, a hammer would strike, or a figure would bow. The Banu Musa brothers, in their Book of Ingenious Devices, detailed the use of conical and heart-shaped cams to create complex, repeating sequences. This was mechanical programming in its purest form. The camshaft was the hardware, and the cam profiles were the software, physically etched in metal. This cam-based control was often married to hydraulic and pneumatic power. Water flowing from elevated tanks through carefully calibrated valves and pipes provided a steady and reliable source of energy. Float valves, similar to those in a modern toilet tank, were used to maintain constant water levels, ensuring consistent operation. Siphons created sudden discharges for dramatic effects, like causing a dragon to roar or a figure to jump. Al-Jazari's famous elephant clock used a complex water system hidden within an ornate elephant model to mark the passing hours, with a robotic mahout striking a cymbal and a dragon nodding its head. The entire system was a marvel of integrated feedback control, where the flow of water regulated the pace of the performance, and mechanical triggers ensured each action occurred in its proper sequence. The conceptual leap these engineers made is what truly staggers the modern mind. They were building open-loop control systems machines designed to execute a predetermined sequence of actions without any external feedback. While they lacked the sensors and microprocessors that allow modern robots to adapt to their environment, they had mastered the art of precise, repeatable motion. A modern car's engine uses a camshaft to open and close its valves in a perfectly timed sequence. The principles at work in Al-Jazari's serving automaton are fundamentally the same. These medieval inventors were laying the conceptual groundwork for automation, exploring how to delegate complex, multi-step physical tasks to a machine. Their work represents a bridge between the static world of simple tools and the dynamic world of self-operating machines. They proved that through the clever arrangement of gears, cams, and fluids, one could encode intention into mechanism, creating a physical echo of human action that could play out again and again with flawless precision. It was a testament to the power of empirical engineering, where breathtaking complexity was achieved not through abstract theory, but through a deep, intuitive understanding of motion, force, and the theatrical potential of a well-placed peg on a rotating drum. Far to the south, in the arid river valleys of ancient Peru, a different kind of alchemy was taking place, one that transformed base metals into objects of breathtaking beauty and spiritual power. The Moche civilization, which flourished between the 1st and 8th centuries, left behind a legacy of metalwork so advanced that it continues to challenge our understanding of their technological capabilities. Unlike the Old World, where iron and steel became the metals of choice for tools and weapons, the Andean world perfected the art of working with gold, silver, and copper, creating alloys and achieving surface finishes that seemed to defy the very nature of the materials themselves. Their most astonishing achievement wasn't just shaping metal. It was fundamentally changing its appearance through a process that we now recognize as electrochemistry, achieved 1,000 years before the battery was invented. The pinnacle of this art form is seen in their ritual objects, particularly the exquisite funerary masks and ceremonial cups. To the naked eye, these artifacts appear to be made of solid, gleaming gold. But scientific analysis using techniques like X-ray fluorescence has revealed their stunning secret. The objects are actually made of a copper-rich alloy, and they are only sheathed in a microscopically thin, perfectly even layer of pure gold. This isn't foil glued or hammered onto the surface. That method would leave seams, would wear unevenly, and could not achieve the flawless, molecular-level bond that these Moche pieces display. The gold is instead fused to the underlying metal through a spectacularly clever chemical process known as depletion gilding or electrochemical replacement plating. The process these master smiths developed was a multi-step ritual of fire and chemistry. They would first create the object itself from a special alloy called tumbaga, a mixture of gold and copper. While beautiful, this alloy has a reddish gold hue, not the dazzling, sun-like brilliance the Moch prized for their deities and elites. To transform it, the artisan would apply a paste of natural minerals, likely ground iron oxide and common salt, to the surface. The object was then carefully heated, not to melting, but to a precise temperature in a controlled fire. This heat would drive a chemical reaction where the copper at the surface would preferentially oxidize. The acidic paste would then dissolve this oxidized copper away, leaving behind a porous, spongy layer of pure gold. This heating and pickling process was repeated over and over, perhaps dozens of times. With each cycle, another microscopic layer of copper was stripped from the surface, and the gold content became more and more concentrated. The final step involved burnishing the surface with a smooth stone, compressing the porous gold layer into a solid, brilliant, and incredibly durable shell of 24-karat gold. The result was an object that had the soul of common copper but the radiant, divine skin of the sun god. What is truly humbling about this technique is that it is a precise, controlled application of the electrochemical series, a fundamental concept in chemistry that ranks metals by their tendency to lose electrons. In any environment where oxidation can occur, a less noble metal like copper will corrode before a more noble metal like gold. This principle is the basis for modern electroplating, where an electric current is used to drive the reaction. The Moch, without any knowledge of electrons or electrical potential, learned to harness this natural principle using only heat and locally sourced chemicals. They were effectively creating a localized electrochemical cell on the surface of the metal, using the heat to provide the energy needed for the reaction to proceed. Their understanding was entirely sensory and empirical. They knew that using a specific mineral paste at a specific temperature for a specific amount of time would yield the desired golden transformation. They could read the colors of the metal in the fire and judge the progress of the reaction by eye. This was not a secret known only to the Moch. Similar advanced gilding and alloying techniques have been found in artifacts from the later Chimu and Inca empires, suggesting a long and sophisticated tradition of metallurgical knowledge that was passed down through generations of master smiths. They also developed complex methods of soldering, annealing, and creating intricate three-dimensional sculptures from sheet metal. The famous gold mask of the Lord of Sipon, a Moch ruler buried with unparalleled splendor, is a testament to this lost expertise. Its flawless gold surface, its detailed nose ornament, and its serene expression were all achieved through this incredible, painstaking process of chemical transformation. These artifacts stand today not merely as pretty trinkets, but as silent, gleaming proof of a scientific mindset that valued deep, systematic experimentation. The ancient metalworkers of the Americas were not just craftsmen. They were early materials scientists, manipulating the very atoms of their world to create a bridge between the earthly and the divine, all without ever writing down a single equation. While the Moch metalworkers of Peru were mastering surface chemistry through fire and paste, a revolution of an entirely different nature was taking place in the minds of scholars thousands of miles away in ancient India. This was not a revolution forged in metal, but one born from pure abstraction, a profound reimagining of the very language of mathematics itself. Indian mathematicians embarked on a breathtaking intellectual journey that would gift the world concepts we now consider fundamental: the number zero, the decimal place value system, and the trigonometric functions of sine and cosine. These were not mere incremental improvements. They were paradigm shifts that shattered previous limitations and created a new, powerful toolkit for describing the universe. Imagine trying to do long division or advanced calculus with Roman numerals. It's nearly impossible. The Indian system liberated mathematics from clumsy notation, creating a flexible, efficient, and incredibly powerful symbolic language that could express vast numbers and complex relationships with elegant simplicity. This intellectual infrastructure didn't just make calculations easier, it made entirely new kinds of scientific inquiry possible. The most revolutionary of these concepts was undoubtedly the idea of sunya, nothingness, void, zero. For ancient Greek mathematicians, the idea of a number representing nothing was a philosophical absurdity. How could nothing be something? But Indian thinkers, influenced by spiritual concepts of emptiness and potential found in Buddhist and Hindu philosophy, had the intellectual courage to formalize this abstraction. Around the 5th century, a mathematician named Aryabhatta was working within a place value system, but it was Brahmagupta in the 7th century who in his text BrahmasphU letter 1e6 DISIDDH Macron NT laid down the first rigorous rules for arithmetic with zero. He declared that a number subtracted from itself is zero, and he even tackled the mind-bending problem of division by zero, correctly identifying it as an operation that defied definition. This was a monumental leap. Zero wasn't just a placeholder anymore, it was a full-fledged number with its own properties and behaviors. This abstract entity became the cornerstone of the entire place value system, allowing for the elegant expression of numbers like 101 and 1000, where the position of a digit defines its value. Without this concept of zero as a number, the smooth machinery of algebra, calculus, and ultimately all modern computing would simply grind to a halt. This powerful new mathematics was not developed in an ivory tower for its own beauty. It was driven by the most practical and profound of human questions, understanding our place in the cosmos. Indian astronomy reached staggering levels of precision, and this accuracy was utterly dependent on sophisticated mathematical tools. The key to their celestial calculations was their pioneering work in trigonometry. Greek astronomers used a cumbersome chord function, but Indian mathematicians, beginning with Aryabhatta, introduced the concept of Ardha half-chord, which we now know as the sine function. They created detailed and accurate sine tables for every degree of a circle, enabling them to calculate planetary positions, predict eclipses, and model the apparent motion of the sun and moon with remarkable accuracy. They didn't just stop with sine, they understood the complementary cosine function and even developed preliminary versions of the tangent. Their methods for calculating these values involved ingenious iterative formulas and series expansions that wouldn't be rediscovered in Europe until the time of Newton and Leibniz. For instance, the Kerala school of mathematics, led by figures like Madhava in the 14th century, derived infinite series for trigonometric functions like sine and cosine, and even for the constant pi, centuries before European mathematicians. They were essentially peering into the heart of calculus, exploring the mathematics of the infinite and the infinitesimal. This flourishing of theoretical mathematics provided the essential framework that enabled the technological marvels we've explored throughout this video. The precise astronomical clocks, the complex architectural calculations for temples, the intricate calendars, all of them rested on this bedrock of advanced numerical and trigonometric theory. The Indian approach demonstrates a beautiful synergy between abstract thought and practical application. They developed profound theoretical concepts not as a disconnected intellectual exercise, but because they were absolutely necessary tools for solving real-world problems in timekeeping, navigation, and cosmic understanding. They sought to create a mathematical map of the universe that was as accurate as possible, and in doing so, they developed a language of numbers that was centuries ahead of its time. Their work stands as a powerful testament to the fact that the most practical technologies often emerge from the courage to first explore the most abstract and fundamental ideas. While the Mach perfected surface chemistry and Indian mathematicians unlocked the secrets of abstraction, the Roman Empire was undertaking a project of such colossal scale and ambition that it would redefine the relationship between civilization and nature itself. To fuel the growth of their million-strong megalopolis and hundreds of other cities across their vast territory, the Romans needed a resource more vital than gold or grain: a reliable, abundant supply of fresh, clean water. Their solution was not to settle near rivers and springs, but to conquer distance and topography, to reach out and bring the water to them. The result was the aqueduct, an architectural network so advanced that it would remain the unsurpassed pinnacle of water delivery for over 1,000 years after the empire's fall. These were not merely channels of stone, they were the very arteries of Roman life, pulsing with the water that supplied public baths, flushed sewers, filled ornamental fountains, and quenched the thirst of a vast urban population. The genius of the aqueduct system lay in its breathtakingly subtle and consistent engineering, most famously visible in the towering arcades that stride across the European countryside. But those graceful arched bridges were only the most dramatic solution to a single problem: crossing a valley. For the vast majority of their length, Roman aqueducts were humble, subterranean channels, carved through bedrock or buried in trenches, carefully shielded from evaporation and contamination. The true marvel was in the impossibly gentle slope or gradient that engineers maintained across dozens and sometimes hundreds of miles. The Aqua Marcia, for instance, ran for 56 miles from its source to Rome, but descended in elevation by only 190 feet over that entire distance. This translates to a gradient of just 1 foot of drop for every 3,000 feet of horizontal run, a slope of a mere 0.03%. Achieving this over such vast distances through rolling hills and across uneven terrain required a level of surveying accuracy that seems almost supernatural. Using an instrument called a chorobates, a massive wooden frame with carefully calibrated water levels, Roman surveyors could plot a course with this minute, consistent drop, ensuring the water would flow at a steady, manageable pace. Not so fast that it would erode the channel walls, and not so slow that it would stagnate and breed algae. This mastery of flow and pressure led to even more ingenious solutions for overcoming natural obstacles. When a deep valley needed to be crossed, the Romans didn't divert the entire aqueduct around it. They built a pressurized inverted siphon. This involved running a closed pipe, often made of soldered lead or specially designed stone blocks, down one side of the valley and back up the other. This seems to defy common sense. How could water flow uphill? The secret lies in the principle of communicating vessels and the conservation of energy. The water, having gained immense kinetic energy from its descent down the first side of the valley, would use that energy to force itself back up the opposite slope, as long as the outlet was lower than the inlet. The Romans had no formal concept of potential and kinetic energy, but they understood the effect perfectly through observation. They even developed specialized, reinforced stone boxes called casella divisoria at the base of these siphons to absorb the tremendous hydraulic pressure and prevent the pipes from bursting. Furthermore, they incorporated sedimentation tanks along the route. These were large, calm basins where the water would slow down, allowing sand, grit, and other impurities to settle out before the cleaner water continued its journey. This attention to water quality shows a sophisticated understanding of hydraulics that extended far beyond simple delivery. Every component of this system was a practical application of fluid dynamics principles that would not be formally described until the work of Daniel Bernoulli and Leonhard Euler in the 18th century. The consistent gradient ensured a steady, laminar flow, minimizing energy-sapping turbulence, a concept later described by the Reynolds number. The inverted siphons manipulated hydrostatic pressure, a phenomenon later explained by Pascal's principle. The use of sedimentation tanks demonstrated an intuitive grasp of Stokes' law, which governs how particles settle in a fluid. The Roman engineers were not theoretical physicists, they were problem solvers. They learned through generations of trial and error that a certain slope produced the best flow, that a certain pipe diameter could handle a certain pressure, and that letting water rest would make it clearer. Their innovation was driven by the most practical of imperial needs: public health, urban sanitation, and the sheer grandeur of a city filled with flowing fountains. They manipulated the variables they could see and measure to achieve a desired outcome, mastering the effects of fluid mechanics centuries before the underlying mathematical causes were ever deduced. The aqueducts stand not as monuments to a forgotten science, but as timeless monuments to the power of empirical observation, relentless experimentation, and the audacious will to reshape a continent's hydrology to serve the needs of a civilization. The terrifying spectacle of Greek fire was not a static invention. It was a technology that evolved dramatically over the 6 centuries the Byzantine Empire wielded it. The initial formula, a fearsome liquid that burned on water, was only the beginning. As their enemies adapted and siege technology advanced, Byzantine engineers were forced to innovate, transforming a terrifying substance into a truly systematic weapon of war. The most significant leap was in its delivery. The early methods of pouring the fire from pots or using hand-operated pumps were risky and limited in range. The Byzantine response was a piece of hardware that would not look entirely out of place on a modern battlefield: the pressurized siphon. This was not a simple tube, it was a complex early example of a projectile weapon system. Historical accounts and artistic depictions suggest it consisted of a heated bronze tank, where the mixture was likely warmed to reduce its viscosity. This tank was connected to a pump mechanism, probably operated by a crew of 2 men. One would work the pump to pressurize the tank, while the other aimed a bronze tube, often crafted to resemble the head of a lion or other fearsome beast. At the tip of this tube, a pilot light would have been kept burning. When a valve was opened, the pressurized liquid would erupt from the beast's mouth in a continuous stream, igniting as it passed the flame to create a roaring jet of fire that could be accurately directed at enemy ships or siege engines from a much safer distance. The engineering knowledge required to make this system work effectively is staggering to consider. The operators had to manage pressure levels within the bronze reservoir too little, and the stream would be weak and short-ranged; too much, and they risked a catastrophic explosion. They were intuitively manipulating principles that would only be formally defined by Boyle's law in the 17th century, which describes the relationship between the pressure and volume of a gas. Furthermore, the entire process relied on a deep, if empirical, understanding of combustion chemistry. The mixture had to be preheated to just the right temperature to ensure it would flow easily but not become unstable. The nozzle design was crucial for creating a coherent stream rather than a useless spray, implying a grasp of fluid dynamics and projection that wouldn't be mathematized for centuries. This was no longer just throwing fire, it was the controlled, directed application of a chemical agent under pressure. It represents one of the earliest examples of a true flamethrower, a weapon that wouldn't see its like again until the horrors of the First World War. This relentless drive for improvement underscores a powerful theme in the history of technology: the role of acute, existential necessity as a mother of invention. The Byzantine Empire was a state perpetually under threat, a Christian bastion surrounded by often more powerful enemies. Their survival depended on maintaining a technological edge, and Greek fire was their ultimate trump card. This military necessity created a unique environment for sustained research and development. Teams of alchemists, engineers, and military officers likely worked in strict secrecy, constantly experimenting with new formulations and delivery mechanisms. They would have tested different petroleum sources, various thickening agents to make the fire stick better, and new chemical additives to increase its intensity or make it even more difficult to extinguish. Each naval engagement would have provided field data: what worked, what failed, and how the enemy attempted to counter it. This feedback loop of theory, experimentation, ND Chinese letter, Chinese letter, Chinese letter, Chinese letter, Shijian Yingyong practical application, mirrors the modern military-industrial complex, but it was powered entirely by empirical observation and craft tradition rather than a formal scientific establishment. The ultimate fate of Greek fire is as instructive as its development. The secret was so closely guarded, so compartmentalized within the Byzantine state apparatus, that it became a vulnerability. The knowledge wasn't widely disseminated, it was held by a select few. When Constantinople finally fell to the Ottomans in 1453, the intricate knowledge of how to manufacture the precise formula and operate the complex delivery systems appears to have died with the last of its keepers. Numerous subsequent powers, from the Arabs to the Crusaders to later medieval kingdoms, tried and failed to replicate it. They could create incendiary weapons, but never anything that matched the reported effectiveness of true Greek fire. Its loss symbolizes the fragility of knowledge that is advanced beyond its time. It wasn't just a recipe that was lost, it was an entire ecosystem of expertise, a continuous tradition of experimentation and refinement that was severed. The weapon that had defended an empire for centuries vanished because its existence was predicated on secrecy, and in the end, that very secrecy ensured its destruction, leaving behind only legends and a burning question about what other marvels of practical science have been lost to the silence of history. Soaring toward the heavens, the great Gothic cathedrals of medieval Europe present a breathtaking paradox of stone and light, appearing both impossibly heavy and miraculously weightless. In an age without structural steel or reinforced concrete, master builders embarked on an audacious quest to reach closer to God, not just spiritually but physically, by constructing the tallest, most luminous buildings the world had ever seen. The driving philosophy behind this architectural revolution was to create a sense of divine transcendence, to overwhelm the faithful with awe by filling vast, cavernous spaces with heavenly light filtered through stained glass. But to achieve this vision of stone lacework and towering spires, they had to solve a fundamental physical problem: how to support a massive stone roof while eliminating as many heavy, light-blocking walls as possible. Their ingenious, empirically derived solutions, the flying buttress, the ribbed vault, and the pointed arch, formed a silent stone skeleton that channeled immense forces in ways that wouldn't be mathematically understood for centuries. The true enemy of these monumental structures was not gravity itself, but the sideways thrust or lateral force generated by heavy stone roofs. A simple, barrel-shaped stone vault pushes outward along its entire length, demanding incredibly thick, fortress-like walls with few windows to contain that thrust. The medieval mason's first breakthrough was the ribbed vault. Instead of a solid, monolithic shell of masonry, they built a skeletal framework of stone ribs like the bones of an umbrella. that concentrated the roof's weight onto specific, strategic points at the corners of the bay. This alone was a revolution. It meant the walls between these points were no longer load-bearing, but the weight was still immense, and it wanted to push the walls outward. This is where the most iconic innovation took flight, the flying buttress. This was not merely a support, it was a sophisticated force transmission device. Imagine a stone arm leaping through the air from a massive external pier to connect with the cathedral's upper wall at the precise point where the vault's thrust was greatest. This external armature acted like a brace, catching the outward push of the roof and channeling it down and away from the main structure, where it was ultimately buried in the ground by the immense weight of the buttress pier. The entire cathedral became a dynamic equilibrium of opposing forces, the vault pushing out, the buttress pushing in a tensegrity of stone that allowed the walls to be hollowed out and filled with the magnificent stained glass that became the hallmark of the Gothic style. Every aspect of this engineering was learned not from textbooks, but from the school of direct experience and, at times, catastrophic failure. The medieval master mason was a practical geometer and a master of pattern books, passing down proportional rules and design templates that had been proven to work through trial and error. They understood structural behavior through a tactile, visual language. They knew that a pointed arch, unlike a rounded Roman arch, could be made taller and narrower without increasing its lateral thrust, allowing for greater height and more slender piers. They learned that the precise angle of a flying buttress was critical. Too shallow and it wouldn't resist the thrust effectively, too steep and it might fail under compression. This knowledge was earned. Many cathedrals witnessed terrifying collapses during construction, particularly of towers and vaults. The partial collapse of the choir at Beauvais Cathedral in 1284, then the tallest structure in Europe, is a stark reminder of the risks they took at the very edge of their understanding. Each disaster was a brutal but invaluable lesson that was studied, and the solutions were incorporated into the next project. They were iterating and optimizing their designs across Europe, with teams of masons moving from one great building site to another, sharing the hard-won knowledge of what worked and what did not. The principles they were manipulating are the bedrock of modern structural engineering: the resolution of forces, the management of compression and tension, and the efficient transfer of loads along the path of greatest strength. Yet, these masons had no concept of vectors, no equations for stress and strain, and no finite element analysis software. Their understanding was entirely intuitive and phenomenological. They could see a crack forming in a wall and understand what it meant about the forces at play. They could feel the stability of a structure through the craft of construction itself. They were conducting a centuries-long, large-scale experiment in structural mechanics, building their theory one stone at a time. The cathedrals that still stand today, having weathered centuries of storms and wars, are not merely beautiful relics. They are the enduring data points of that experiment, proving the validity of their empirical genius. They represent a pinnacle of pre-scientific engineering, a testament to the power of human observation, craftsmanship, and the courageous desire to build the impossible, reaching for the divine light long before they could fully describe the physical laws that made it all stand. These 28 forgotten marvels from humanity's past reveal a profound and humbling truth about the nature of discovery itself. They show us that the path to innovation is not a straight line from theory to application, but rather a messy, beautiful, and often circular dance between observation and creation. Long before the formal language of physics and chemistry existed, ancient minds were already speaking the dialect of the universe through their hands, their tools, and their relentless curiosity. The Antikythera mechanism's bronze gears calculated celestial movements without a theory of gravity. The makers of the Baghdad battery may have generated a current without any concept of electromagnetism. The builders of the Inca walls understood seismic energy dissipation centuries before the science of structural dynamics was born. They didn't need the textbook because they were reading directly from the world itself. This incredible history fundamentally challenges the modern, often arrogant, assumption that technological superiority is a linear progression. We tend to view the past as a simpler time, a prelude to our own enlightened era of scientific understanding. But these artifacts stand as silent, powerful rebuttals to that narrative. They force us to ask a much more interesting question, not what did they know, but how did they know? The answer lies in a different kind of intelligence, one built on deep, patient observation, on generations of carefully guarded craft knowledge, and on a willingness to experiment relentlessly. It was an intelligence of the hands and the eyes, honed by immediate practical need. A Roman engineer didn't need to understand the molecular reaction behind pozzolanic chemistry to know that mixing a specific volcanic ash with lime and water created a concrete that could set underwater. He just needed to build a harbor that would last. A Viking navigator didn't need a wave theory of light to understand that rotating a calcite crystal until two images aligned would point him toward the hidden sun. He just needed to find his way home through the fog. What is perhaps most remarkable is how many of these devices were not one-off flukes, but the peak of long, sophisticated traditions. The Antikythera mechanism implies a lost history of Greek-geared devices. The self-healing Roman concrete formula was used for centuries across a vast empire. The Mayan astronomical tables represent generations of unbroken celestial observation. This suggests that these were not isolated sparks of genius, but sustained fires of innovation that burned brightly within their cultural contexts. Their light was eventually dimmed by war, cultural collapse, or the simple fragility of knowledge that is passed down orally or held by a small elite. The loss of these technologies is a stark reminder that progress is not inevitable. It can be forgotten, its threads dropped from the loom of history, only to be painstakingly rewoven centuries later. Ultimately, these 28 devices are more than just historical curiosities. They are a testament to the boundless potential of the human spirit. They remind us that innovation can spring from any time and any place, driven by necessity, wonder, and a deep desire to solve the problems right in front of us. They show us that we can harness the laws of the universe long before we can name them. So the next time you look at a modern marvel of engineering, from a smartphone to a spacecraft, remember that it stands on the shoulders of a much older, and in many ways just as profound, tradition of ingenuity, one built not on abstract equations, but on watching the world with keen eyes and daring to ask, what if? If this journey through the shadows of history has sparked your curiosity, we'd love to hear which of these forgotten devices most captured your imagination. Was it the celestial computer of the Greeks, the self-repairing concrete of the Romans, or the nano-forged steel of Damascus? Share your thoughts in the comments below, and be sure to subscribe for more adventures into history's greatest mysteries.